Performance characteristics. As we have discussed the procedure of the size reduction, also we have discussed the different size reducers, different devices like hammer mill, iteration mill and crusher. Now how we will evaluate the performance of the different devices. Okay, suppose if two different hammer mill is working, reducing the size of the agricultural product, so how you will evaluate the performance, that which one is better than another one. Okay, so the most important factor to which we are looking, that is the uniformity of the product. Okay, the size of the product which is reduced, okay, we are looking into its uniformity. Okay, let's see, the size of the reduced particle will be uniform. Okay, so uniformity of product depend on number of hit. Since the path of travel of a grain through the grinder is random, so the number of time a grain hit varies, and as a result the size of the product varies. Okay, see, when an individual grain, suppose that is hitted 5 times, and another grain, suppose it is hitted 8 times, so it will be reduced more finer than this one. So it means that if each and every particle, if the agricultural product is hitted by same number, then the reduction will be uniform. And the energy dissipated upon contact between a grain and a hammer varies as the square of the velocity. Okay, the energy dissipation, see, when the product is hitted by the hammers, so some heat will be generated, some that the kinetic energy of the hammer will be dissipated in disintegrating the product. Okay, and that energy dissipation is varies the square of the velocity. Okay, mean when the rotator, when the hammers are rotating at higher velocity, then the contact of the grains will be more with the hammers. Okay, and the product will be reduced more finer. So a grain that hit near the, and also see, the hammer has some distance from the shaft, so the grain which hitted near the end of the hammer, it will be more finely divided as compared to the one hitted close to the shaft. Okay, so when the particle are uniformly or more hitted by the head of the hammer, then it will be more finely reduced. And the gradation mean the variation in the size, that is a function of the material to be reduced in size by grinding, not the grinding procedure. Okay, mean the variation in the sizes after the reduction, that is the gradation, mean the variation in the sizes. Okay, that will be the function of the material, that which type of material you are reducing. Okay, either it is fibrous material or dry material or sticky material. So we can say that dry material will be more uniformly reduced as compared to the fibrous material, because there is some moisture content, so then it cannot be properly and uniformly reduced. The iteration mill produce more uniform product than the hammer mill, and that is also the advantage of the iteration mill, that it produce uniform product. The second factor is the power requirement, that how much power is required for the size reducer. Okay, so see, if more power is required and it is reducing less product, so its performance will be less, it will be least efficient. Okay, so also the power requirement is depend on type of material. Okay, for example, fibrous material like barley, it require more power than the crystalline material. Okay, corn, that is a type of dry product, that is a type of dry agricultural product, this is a type of fibrous agricultural product. So suppose if you are reducing the size of these two products up to similar reduction, okay, then more power will be required for barley as compared to corn. So we can say that fibrous product required more power as compared to the dry product. Moisture content, again, if there is more moisture content in the agricultural product, then it will be not properly reduced as compared to the dry product. Okay, fineness of grinding, again, suppose if you have to reduce the product if you have to reduce the product up to the more fineness condition, then more power will be required. And if suppose if you have to roughly reduce the size of the product, then less power will be required. Okay, rate of feed, again the product which you are entering into the hammer mill or attrition mill or crusher. So if rate of feed is more, then again more power will be required. Okay, type and condition, power is directly varied with the speed. If you are increasing the speed, the number of head will be increased, fineness will be increased, but more power will be required. And see, 8 times as much power would be required to operate the fan at 4,400 revolution per minute as it is to 2200. Suppose if you doubled the speed, okay, suppose if you doubled the speed, then 8 times of more horsepower will be required. Okay, suppose, so it means that if you are increasing the speed of the hammers, if you are increasing the speed of the shaft, then more power will be required. Okay, and the mostly the power requirement or the energy requirement per particle size reduction is the function of input and output particle size. Okay, the particle of which size you are reducing, suppose its size is d1, and see suppose the size is reduced to d2. Now how much power will be required? Okay, so the power requirement is depend on the initial size, the final size, the hardness of the product, strength of the product, and other properties, moisture condition, shape and size, etc. But most importantly, the power requirement is depend on the size of the product before reduction and after reduction. Okay, so mainly we have 3 different theories which is used for the determination of energy requirement. The Rittinger theory, it states that energy required per size reduction is proportional to change in the surface area of the pieces of food. Okay, suppose if you have food product, so what is its surface area before the size reduction and what is its surface area after the size reduction? Okay, and numerically we can say that the energy requirement by Rittinger theory, the energy requirement is equal to Rittinger constant multiplied by 1 divided by d1 minus 1 divided by d2, where d1 is the size of the particle, sorry, d2, and this is d1. d1 is the size before the reduction and d2 is the size after reduction. Okay, then we have the Keck's theory. Remember, the Rittinger theory is mostly used for the fine particles. Okay, for the fine reduced particles, mean if the product is reduced up to the fine condition, up to the powder form, then the energy requirement will be equal to Rittinger constant into 1 over d2 minus d1. Okay, the Keck's law, that is mostly the Keck's law is mostly used for coarse product, yeah, per coarse material, if the size is not too much reduced. Okay, and it say that the energy required to reduce the size of particle is proportional to the ratio of initial size of a typical dimension to the final size of the typical dimension. See, the energy requirement by this law is equal to, again there is some constant which is called the Keck's constant, and ln of d1 divided by d2. Okay, ln of d1 divided by t2. Here the, remember, the energy will be in joule, d1 and d2 will be in meter. Okay, and this kk, that is the Keck's constant. Okay, and that is suitable for coarse material. Bond's theory, that is suitable for intermediate material, and it say that energy required per size reduction, energy per unit. See, this W is called the bond work index. Okay, bond work index, and its value is normally varies between the 40,000 to 80,000. Okay, again it is a type of bonds constant, but it is called the bond work index. So energy per bond work index is equal to under root 100 divided by d2 minus under root 100 divided by d1. Okay, so this is the bond law. So these are the three laws which is used for fine reduced product or coarse reduced product or intermediate reduced product, and these are the energy requirement. And remember, energy requirement will be in joule, d1 and d2 are in meter, and this kr is Rittinger constant, kk is Kick's constant, and this w, that is the bond work index. Okay, and its value is in between 40,000 to 80,000. Okay, now see, for example, if you are reducing the size from 6 millimeter suppose to 0.0012. okay, suppose d1 is 6 millimeter and d2 you can see suppose that is 1.2 millimeter. Suppose horsepower requirement is 10. Okay, suppose we have a machinery in which we are reducing, suppose we have a mill or suppose we have attrition mill or hammer mill in which we are reducing the size from 6 millimeter to 1.2 millimeter. The power requirement is 10 horsepower. Now suppose if the size is reduced up to 0.8 millimeter, okay, so how much horsepower will be required? Okay, if the size reduction is up to 0.8 millimeter, then how much horsepower will be required? So by Rittinger theory, first find out the Rittinger constant. See, if the energy requirement is 10, then we can say that the Rittinger constant will be equal, energy requirement will be equal to Rittinger constant 1 divided by d2, which is 0.0012 minus 1 divided by 0.006. okay, so first you will get the Rittinger constant, you will get its value, for example x. Okay, now suppose if you have to reduce the size from 6 millimeter up to 0.8 millimeter, so how much energy will be required? So energy will be equal to that Rittinger constant 1 over 0.8 millimeter, so that will be 0.0008 minus 1 divided by 0.006. okay, so approximately then 15 horsepower will be required. Okay, so just meaning of this example is if you have to reduce the size from 6 millimeter to 1.2 millimeter, then 10 horsepower is required. And suppose if you are reducing the size from 6 millimeter to 0.8 millimeter, then 15 horsepower will be required. Okay, so the power requirement is depend on the initial size and final size of the product. And the third factor, that is the temperature rise, which is used for the performance evaluation of an size reducer. Okay, so the one which is suppose generating more heat, it will be less efficient as compared to the one which is generating less temperature, less heat during the size reduction. So see, the energy per grinding the product is dissipated at heat energy and raises the temperature. See, suppose we have the hammers, so hammer will have some kinetic energy. That kinetic energy will be applied to the product on hitting it. Okay, some hit force, impact force will be applied on it, and as a result what will happen, the product will be disintegrated and the temperature will be raised. Okay, inside of the environment the temperature will be raised, so heat energy will be lost in vaporizing the moisture sometime. If there is some moisture content in the product, and suppose during the disintegration, for example, if the temperature is raised, so the moisture content will be evaporated. Temperature of fibrous material rises more as compared to the crystalline material, which we have discussed. Like we have three types of product: fibrous, sticky and dry. So fibrous material rises, temperature of fibrous material rises more as compared to the dry product. Okay, the hammer mill produce a cooler product because the hammer mill have open casing. Okay, so the temperature generated there will be easily circulated in the surrounding. Okay, while the temperature generated in the attrition mill, it cannot be circulated into the outside environment, so it can increase the temperature of the grounded product. And high temperature contribute to the decomposition. Now remember, for example, if in attrition mill the temperature is raised, so what will happen? Inside, the decomposition of the product will be started. Okay, and suppose if there is moisture content, then the product can be damaged. So remember, whenever you are selecting any type of size reducer, so you must be making ensure that how much temperature will be raised, and is there any kind of recirculation facility, okay, so that the product may not be damaged. Here you can see that the temperature of different product which can be raised if you are reducing its sizes. For example, oats. Okay, so suppose if you are reducing its size in burr mill up to the finest modulus of 2.73, so up to 50 degree Fahrenheit its temperature can be raised. And suppose if you are reducing it with the hammer mill, so it can be reduced up to the finest modulus of 2.70, and the temperature raised will be 18 degree Fahrenheit, because there is the recirculation of air, because its casing or housing of the hammer mill is open into the surrounding. Similarly, barley, if you are reducing it with the burr mill, okay, or if you are reducing it with the hammer mill up to this much reduction, the finest modulus is showing the fineness of the product, that how much you are reducing the size. So here you can see that the temperature at the burr mill will be increased more as compared to the hammer mill. Okay, so these are the different characteristics through which we can evaluate the performance of an reducer. Okay, uniformity of the product, temperature rise, and power requirement. Okay, so this was all about the size reduction, which is the main and important agricultural processing operation. Okay, thank you.